Today we are covering the cascode stages and current mirrors. What is the ideal output resistance of a current source, of an ideal current source? Having an ideal current source, think about Norton. We represent the current source usually with a shunt resistor, and then we connect the load resistance here. So the current source.
Oh, understand. Infinite.
Yeah, it should be infinite, right? Because we don't want currents flow to this resistance, but we actually want the currents flow that resistance to the output resistance. So if we model the current source with a Norton representation, that will give you the answers. And that's what we'll be doing for half of the lecture today. So we are trying to provide good representations of this current source. And the best way to do that is using Cascode stages. That's why we are covering Cascode stages today. And then after we get a good current source, that's what matters. After we get the source, we'll mirror them and we'll get that duplication to be used in rest of our chip or our circuits. So what matters is to come with that golden current source. So this is at the left a BJT representation, a BJT circuit, and at the right is a CMOS circuit. So and last lecture, like also as well in 301, we went through the output resistances. So when we go and try to find the output resistance of a circuit, we draw the small signal model of this BJT or the CMOS, whatever circuit is given to you. And to do that, for instance, if you look at this circuit, just the BJT one, as you can see, we just draw the small signal representation of the BJT, like here. And then to find the R out, we connect the test source and we find Vx over Ix. So we write some nodal analysis and we find Vx, then dividing Vx by Ix, we find R out, and then you get the simplification. And as you can see, the R out of this circuit, the BJT one, is RO resistance, which is this resistance due to the non-idealities, which we call it channel length modulation, times 1 plus GM times RE in parallel with R pi. So RE in parallel with R pi, right? And there is a GM function here, transconductance, but the big impedance is basically due to the RO, because RO is 1K or sometimes 2K, depends on the VA value of the transistor. So going back to the original slide here. So as you can see, for JT and for CMOS, this R out can be different. Why can be different? Because in BJT, we have R pi factors, but in the CMOS, we don't really have any R pi, right? Because therefore, the R outs might be slightly different. So one of your probably first prelapse will be, hey, compare these two circuits or maybe more complicated ones and figure out which R out is bigger. And as we've discussed in the beginning of the lecture, to get a good current mirror, we want this R out to be infinite. The derivation for the R out here for the BJT is at the right. For the CMOS, you can also find it. So if we look at the Cascode stage, which again we covered in 301, we will see that this R out resistance gets much bigger, because now previously we were looking at this R out, But now we stack, it's called stacking. We stack another transistor and made this a cascode transistor or amplifier. And now the reason we did this is because we brought much more isolation to the circuits. So bringing this Q1, so you are isolating basically this transistor even more. So that's kind of boosts your ROUT. So how is it boosting your ROUT? Well, this transistor basically is, if you draw the small signal, there is a ROUT here, like RO here, and then there will be an R pi here. And you'll see that in the small signal, okay, well, I didn't attach the small signal model, but you'll see that the ROUT will make this this RO of this transistor will make the ROUT much bigger. So compared to the original one, let's just figure out the differences. Look at this circuit and let's look at this circuit. And as you can see, the ROUT for this is this one, and ROUT for this, for the Cascode, is this one. So what differences do you see?
RO2 turns to RE.
Right. Well, in this one, there is no RE. So assume RE is 0. So assume this one is 0. So 0 parallel R pi will be 0. So this will even, don't even think this one is, is there. So, but you are right. Important thing here is as I mentioned, this Cascode stage is now boosted by R. So if the Q1 wasn't there, we would be seeing this one. Basically, the circuit will be this one. But now when we add the Q1, what is happening is the resistance is now getting boosted by ROUT1. So when you do the small signal analysis, you'll get to understand, yourself much better why and how. But as I mentioned, you are stacking these transistors and increasing the output resistance. So that's why we are using cascodes. It's much bigger compared to this term. So, and we can simply take this part as the ROUT because the second term is much smaller compared to the first term. Hey, we have this cascode circuit, and you are given in the circuit that ROUT is this. It's already given in the hint, in the question, put all the values, the ROUT is this. If you do this question with only one transistor, which I explained it in the beginning, assuming the RE is 0, well, you wouldn't even come closer to this value. You would probably get like maybe 25K or 30K. And as a practice, you can do it. Long story short, the good thing about cascodes, providing a current mirror is important because you boost your output resistance. And for an ideal source, close to be ideal source, you want this resistance to be as high as possible. So this also can be seen as one transistor, as you can see here attached, and you can just write the equivalent resistance you see here. So this resistance just written simply as RO2 because you see a RO2 here, and you can simply do a small signal analysis and you'll see that the equivalent representation will be this circuit. So it is a representation of a cascode. So what is saying that instead of the transistor Q2, normally there was a Q2 here, right? The other transistor. So instead of that, I assume that's also already a good current source. Well, it's not because the output impedance is not infinite. But assuming it's good, so I just put a current source here. And now I'm looking at that representation, finding ROUT. And when I do that, we know that ROUT is this. right? GM1 times RO1 times R pi 1. And if I go back, GM1 times RO1, and as I mentioned to you, R pi is much smaller. So we just neglected this. So this is ROT for the Cascode. So the interesting thing is GM1 times R pi 1 becomes beta. So this will tell you Cascode output resistance will actually depend on my characteristic of my transistor. If the beta 1, which is IC over IB, basically amplification factors of your semiconductor. This is a semiconductor device. So if you create a really good amplifier, which means a good, like a huge beta, then that means also that you are boosting your ROUT. Basically, R pi times your transconductance is basically limiting your ROUT. So your output impedance, your ROUT, will be always bounded by the R pi. If you become a designer, like a system designer, you will be hearing terms such as, hey, what is the impedance of the internal node? What does that mean? Well, so this is an internal node. There is this transistor here, and there is this other transistor, right? The internal impedance, well, you should ask, which way we looking at? Are we looking this way or are we looking this way? Well, if they don't tell you, then you should look at it overall. Well, there is a path here, there is a path here, and there is a path here. So when you draw the small signal, as I drew like a few minutes ago, there will be a R pi resistor, there will be a RO1 resistor, and then there will be a RO2 resistor connected to this node. Well, I'm grounding this for convenience. So there is a R pi here, there is a RO1, and there is a RO2. Which one would dominate the impedance? R pi, right? Because it's the smallest one. So in other words, this node is not a really high impedance node. This node, due to the R pi, 1 over GM at some point, basically it's a low impedance. So, and this term of low impedance, high impedance will be important. It will be important because, for instance, for an amplifier, we provide the input signal, and the purpose of this amplifier is to amplify the input signal and get gain, right? And now we want to see gain here. Like, let's say this is 1 millivolt. We want to see 50 millivolt here because this is amplifier. So we have an input voltage and we amplified it. We got it 50 millivolt. So do you think this impedance should be like basically equivalent impedance seen here should be high impedance or low impedance? So let's draw the small signal. You have an input source in 1 millivolts. So this goes to basically your base of your transistor. This is base. There's a R pi here, and this is ground. We have a current source, which is BE. We're getting V in, multiplying with GM, we're getting a current here. And this current now is getting multiplied with a purple resistor. Intrinsically, it is RO if there is no external resistor. But if you connect another resistor, then it will be in parallel with that RO, right? Now we have this current, a portion of this input voltage, and we want this current to be multiplied with this resistance, right, to get voltage. So do you want this resistance to be high or low? High, exactly. So that's what we are talking about, high impedance. We want this impedance to be high so that we can get a good voltage swing. And exact point is for Cascode. The entire point of Cascode is to get R out impedance to be high, okay? So if we don't connect Cascode, R out will be small. We add another transistor, we do the small signal analysis, and we see that R out becomes big. But what if I connect a short here? For instance, this might be a good exam question, right? Now, this was your equation. R pi is coming here. Now, there will be another parallel, and it will be 0. So this will go to 0. This will go to 0. Well, this will be only RO1. So probably your R out will be RO1 plus R pi is much smaller than RO2 plus R pi 1. Well, R pi 1 is much smaller than RO1. So your R out will be RO1. Well, it makes sense, right? Because now what we did is connecting that part to ground. We basically ignored this entire circuit. Well, it makes sense because now, it makes sense in terms of what we solved because what we see is only R out 1. We're only seeing this resistance. And when you design a chip, these are the things you deal with because actually in a cascode, this is not, of course, ground here, but in an actual circuit, you will see a capacitance here. That's called parasitic capacitance. And this parasitic capacitance at very high frequencies, let's assume that you are designing a circuit, CMOS imaging, at 100 gigahertz. Well, what is the impedance of this cap? It's 1 over j omega c. So omega is 2 pi f, which means f is 100 gigahertz. So if this cap is a big cap, the frequency is also big, this term will be big. So 1 over that big term will go to 0. So then now you are losing your cascodes, which is not what you want. Well, if you want to get rid of cascode, you wouldn't design it at the first place. Basically, this is a killer node. You don't want this node to be such low impedance. I attach the R pi here to make it a different circuit. Okay. And the question is, what is the new R out? So I told you, hey, this circuit is this, the one in blue. Now I attach this resistance and I want to find a new R out. You can either use your intuition or you can, which I prefer you to do, is you can go draw the small signal for Q2, Q1, and then you find R out 2. So false cascode means some circuits might look like cascode to you, but they are not actually cascodes. For instance, this is a question again from the book, and it explains nicely, the equations. There is this cascode transistor, Q1, basically it's stacked, but watch out the Q2. Q2 is a PNP, it's not a NPN. Well, how do I know it's a PNP? The current is this way. So this is actually emitter here, and this is collector. And what we want to see at this node, I mentioned to you, I want to see a high impedance. Well, if I connect it this way, the impedance I see is not really high because, as you can see, this is a PNP, and the impedance I see will be here. Oops. I will be seeing a 1 over GM. I will be seeing this impedance, this impedance here. So what matters is you want a collector here, not an emitter. Well, we don't want to have 1 over GM here. We want to have RO2 here. I am, instead of this, now I am drawing this. So the transistor is here, and this is the collector, and then there is the base there. So then there's R pi resistor here, then there's emitter here, then there's RO here, then there's this current source, okay? Well, as you see, I isolated this. I don't even see R pi, it's far. So this will be open because it's short. This is 0, 0, the voltage on this. So all I see is RO2, okay? Do you understand the difference? This was a really good slide to explain. Well, so just like BJTs, there are also MOS cascode stage. Now we don't have the R pi because in MOS small signal, there is no R pi, right? This is open here rather than having an R pi. And there is a current source here as well. There is a RO here. So it's very similar to the BJT. but because we don't have RPi, we don't see it in the equations. The end equation becomes this. But if we look at if I bring you a BJT cascode, and as you can see, the equation is GM1 RO1. Well, we have GM1 RO1, but here RPi dominates. So this has become yes. So now we don't have RPi, so we see RO2. Which circuit has higher output impedance? A BJT cascode or a CMOS cascode? This one is BJT and this one is CMOS. The first two terms are same, GM1 RO1, GM1 RO1. The second term, RO2 parallel RPi1 and RO2. Which term is bigger?
Second one.
Yeah.
Right? I mean, here you are attaching another resistor and it makes it smaller. You don't have RPi. There is no RPi here. We don't have it. So it's almost 10 times bigger than the BJT. And
Okay.
that is awesome. And the reason is because in this node, in this middle node, in the CMOS, you don't really have that low impedance. Normally in BJT, you were seeing this RPi, but in CMOS, you don't have it. So this impedance is much higher. And if you look at the voltage at this node through an oscilloscope in the laboratory, you would be seeing that, this node has a much higher swing. Just like I gave the amplifier example with IPEC, there was a small signal here. Here, you should see a high input swing. And if this impedance is low, like the one in BJT, because we have a RPi bringing this output impedance, the impedance at this node to smaller values, then your voltage will be smaller. So the equivalent impedance in this node is important to get a higher voltage here, okay? At 100 gigahertz, that node becomes very critical because there is parasitic capacitance. Parasitic capacitance means these transistors have their internal capacitance because this is CGS, this is CGD. So there are internal capacitances, parasitic capacitances due to these transistors. So now there's a cap here, there's an inductance here. You learned I hope, in 202 that this is a tank. A tank is just like the name. It might be dangerous. Why? Because this is a resonance circuit. At some point, when we look at the output versus frequency, you'll see something like this. And if you operate this circuit at this frequency, okay, let's assume your current source or your voltage source, doesn't matter. You have a source operating in this frequency. And now it hits this tank. Well, what happens at this output? So your output will be huge. So even this is a very small cap, let's say it 1 micro or 1 nano, your output will be Q times V, quality factor times V. And because there is no resistance here, I assume this is infinite. There is no resistance. The Q will be quite big. Well, it depends on the cap and inductor quality because they are the dominating factors. We are looking at these circuits at very low frequency right now, but this Cascode circuit is also used as an amplifier. In this question, it says, due to manufacturing mistake, somehow a parasitic resistor showed up like this. And what would be the new Rout? New Rout, you can just see that this RPi resistance comes with the RO1, right? There is a RO1 here due to the M1. So it comes in parallel with that. New Rout becomes this. And this RPi, if it is small, it will dominate it, right? So then if it is small, this will disappear. And as you can see, your Rout will get smaller. The circuit can be a little bit more complicated. So what if connecting the circuit to another circuit at this node? So when you draw the small signal, you'll see that the you treat the cascode like one arrow here. You already know how to solve it, but now you also need to solve this R so that the R1, and let's call this R2, becomes in parallel. Looking into this circuit, well, this is just a PNP, and this is emitter. Here is collector. If it's an emitter, it's a low impedance. If it's a collector, it's a high impedance. So looking in the circuit, if you draw the small signal, you'll only see RO3. So we can basically redraw the circuit. Your circuit will be RO3 in parallel with your cascode resistance, which we already derived it before. Another practical cascode stage. You might ask, why are we connecting this transistor here? So why aren't we connecting directly this transistor, this cascode to VCC, right? Well, we can, but if we just connect a resistor like this, there will be a current here, and this current will cause a voltage drop. So if this voltage VCC, let's say 12 volts, well, in actual today's technology, it is 1.5 volts, but let's go 10 years back. It's 12 volts. So let's assume this current here is 10 milliamps. We need to keep this RO3 big, right? Let's assume we should keep it 1K because we want RO to be big. Well, 10 milliamps times 1K is 10 volts. Well, if this is 12 volts, this is 10 volts, here will be 2 volts. Well, the 2 volts is extremely small. What does that mean? Well, if we have a swing here, and this being 2 volts, there will be some issues, assuming that this gets amplified, this small signal, around 2 volts DC. Let's assume it got amplified. Well, so let's assume this became 3 volts here and 1 volt here. First of all, if this becomes 1 volt, at some point, maybe even less, this transistor will stop working. We want these circuits to be working at certain values at VC. So let's assume maybe like 0.3 volt, assume. Maybe 1 volt will be enough, maybe 0.5. So at some point, if this drops, then this transistor might go off. Because due to these swings, as I mentioned, this transistor will stop operating at some point. At the top level, at this part, probably currents will also have some linearity issues, which is another issue. Again, we don't want to lose headroom. So this is called headroom. We don't want to lose 10 volts on a resistor. Rather, I use a transistor and I use 3 volts and just see the same resistor, which is RO3. That's why we use transistors actually as well to implement, such big resistors. Put a resistor, eats your headroom, eats a lot of power consumption as well. You don't want to just put a resistor there and have this entire current go through the resistor and dissipate heat. We hate heat, right? We don't need heat in a iPhone chip, laptop. So we don't use resistors in IC design. That's why we use transistors. The circuit can be even more complicated, and we can cascade them. And the reason we are doing another cascade is we are increasing this resistance. If there is only one transistor, the resistor R out would be smaller. Now we added another one. This one increase. This one increase. Well, can we add another one? VCC. Well, we can, but now, as I mentioned, the issue is becoming headroom because all these transistors are getting from your headroom. So the headroom will be discussed more in details, but there's obviously a limit, and it doesn't really bring much more advantage than needed, because if I need, let's say, 5K, why would I get 50K adding more transistors anyways, right? And as you can see, these are PMOSs because current is getting into the circuit. PMOS shouldn't really confuse you, What matters is this node should be connected to a drain or in BJT in a collector. We want this node to be high impedance. If it is connected to a source in the CMOS or emitter in the BJT, then your impedance will drop. So as you can see, it's drain here, it's drain here. And their parallel will be the impedance we see from here. So I will jump to the concept of current mirrors. Current mirrors are important because we wanna duplicate a current signal through the chip. Let's assume a simple circuit. We have a BJT, we have a voltage, VCC supply, we have a voltage divider. Let's assume this is 2, let's assume this is 1, and let's assume this is 12 volts. And this volt will be 4 volts. So the question is, when we design the circuits, actually, these resistors are not really 2 or 1. This might be 1.2, this might be 1.9, or vice versa. Then this 4 volts won't really be 4 volt anymore. This is a process variation. And similarly, there is thermal variation. Your saturation currents for this diode can change. Your thermal voltage might change, and so on. So both for MOS and BJT, we want the circuits to be perfectly designed, which is the current source, this I1, won't be changing with all these different voltage variations, maybe thermal variations, process variations. Basically thermal variations means temperature variations. These equations are not good because, as you can see, changes will cause changes on I1. If VDD changes, I1 will change. If VT changes, I1 will change. We need a golden source. So assume that we have that golden source right now. I'm not discussing how to design that source yet, but we have that source, golden source, that provides a IREF, which doesn't change with anything else. And the current mirror's purpose is to get that IREF and to copy it. So basically, we are able to copy this IREF versions to everywhere in our chip. We can use it here. We can use it here. We can use it here. Okay. Since we designed this once, we can duplicate it other locations. So now we will show how we design those current mirrors. So how we can create these different versions. So while we are discussing how we can duplicate it, we are also looking what are the ways that basically produce minimum change. Because let's say our IREF, golden current source, is 1 milliamp. Well, if you want to double it, make it 2 milliamp at some point, we don't really want it to be 2.1 either, right? We want to double it perfectly. There is this term called diode connected transistor, which when you connect a collector and a base together, you are making it diode connected. And the reason it's called diode connected is because there's a diode here, right? Just like there's a diode here, then there's a diode here as well. So connecting this collector and base together, creating a circuit that is always working in this region. This is BJT. You are always making it work at this region. And the reason is this is VBE, and VBE becomes equivalent to VCE. Şimdi diode connected'ı anlatıyorduk. We have circuits. We connect the collector to the emitter. I'm sorry, collector to the base. You can see here, collector to the base. So when we do that, what happens? VBE becomes VCE because now base and collector are same voltage. Okay, so that's why it's called diode connected. So what would be the VCE for this circuit, just approximation, how much volts would be around for a silicon diode, 0.7, around here. Basically, doing it diode connected carries your VCE from possible low values to around fixed value, like maybe plus minus 0 point something, okay? So that means you are in linear mode where your current doesn't change. In MOS, this is called saturation. In BJT, this is called linear. And that's what we want. We want this current not be changing much, right? Because this is your IREF. So you are already forcing this current. Actually, now this is a trick. You are not really creating a voltage source. You are actually forcing a voltage here because you have this golden current source. Let's assume this one. It is 10 milliamps. When you push 10 milliamps to the circuit, you are forcing a fixed voltage to show up here. Let's say 2 volts, because there is a size of this transistor, IS and stuff. So now this 2 volts will show up here as well, right? Because we connect in series like this way. And now this is ground. This is ground. So same 2 volts will show up here. And depending on the size of this transistor, because for these BJTs, IS matters, right? The formula is IS times exponential VBE over VT. Basically, this is your IREF, and that forces a base emitter voltage. This base emitter voltage shows up here, and now you might have a different IS or same IS, and then you have the copy current, which is same but with a different IS. So that is the current mirror. We actually explain it in 301, but now we'll dig into it a little bit more detail. This is a good question, but I can give you some tips. So it's saying that without shorting the collector and base, if I give you the circuit, what would be the I copy? So it says I copy would be 0 because there will not be a path for the base currents to flow. So normally if we connect this, the base current will flow here. Anyways, in PSpice, you can play with this and you can understand the importance of the diode connection. Well, as I mentioned, you can take this reference current and you can distribute it to different parts of the chip. So with multiple copies, you can bias different parts of the chip without really relying on different bias circuits. Okay, another question. This is a diode connected BJT. The I copy actually will be dependent on your beta at some point. We are assuming here beta is infinite, like previously it was huge. So this would be 0, and your copy would be, if this IS will be n times, which is scalable to the area, so then you would be seeing an IREF. But if your beta is not huge, but if it is something small, then now you have some non-ideal situation, right? So now this term will affect your I copy currents, because the base current here is actually what matters. What we are copying here is before the collector currents, we are actually copying the base current. So this is I copy divided n beta. So this entire circuit is actually copying this base current and scaling it by n. And that's why we get to see the I copy here. All right, so, and the reason is because there will be some currents of these two. This is I1, this is I2. And now when you sum these up, that current comes here. And then this current minus this current will be flowing here. and you can see that, you know, it affects your circuits. Okay, so instead of this short, we are connecting this buffer transistor, and when we do that, improving the accuracy, because if you look at the previous design, the accuracy was highly dependent on the beta. Like if the beta is small, then you won't be getting an IRF. So now let's look at this circuit. The accuracy improved. Well, how we got the B square actually, okay? B is small, well, B square will be still large. So this will go to 0. So you will be still getting an IRF. These two currents, this one and this one, is now the sum of them is this current, right? Just like the previous circuit. But now this current is IC. So this current being IC, so let's call this, well, let's call it IX, for instance. Well, this current will be IX over beta F. So let's assume their betas are same for this transistor as well. So then it will be IX over beta. Well, as you can see, this one even got smaller, right? So now our RF minus this current will be still very close to RF. So in the previous circuit, as I mentioned, these currents were affecting. How they were affecting, these two currents are here, you know, they are this plus this basically is going through here. Well, now because this is going through here, this current is not IRF anymore. It's something less than IRF, this much. And now this was causing this issue. But now in the other circuits, that current become much less, because now we made that current even smaller by providing another transistor and having that current divided by beta. So that's why another beta factor comes here, and this current becomes very close to the IRF. So again, if you look at this circuit, what we care is this is ground, this is ground. They are sharing the same base, so their VB is same. This is saturation current IS. Well, if this is NIE, their saturation current will be NIS. What we want to copy is this current. So in other words, this base voltage VB is created by this current. So we want this current to be IRF. That's why it's important not to lose current here. That's why we use that transistor. Because now if we have IRF here, we create this IRF pushes this VB to be a value, and that value will be transferred here. And now we will certainly and nicely copy the IRF using saturation current of the diodes. And this IS is a strong function of the area of the diode. That's why if this area is AE and this is NIE, the saturation current will increase by basically N times. Well, same logic with MOS, exact same stuff. Instead of the IS, what matters is, because of the MOS equation, what matters is omega L, right? Because the current is K times VGS minus VT square. K is COX times UX times omega over L. So what really defines your circuit current is this. So if you have the same VGS, well, you have same VG and S is ground. So for all these circuits, you have the same VGS. So if you have same VGS, what matters is, because the C is same, mu is same, what matters is omega over L. And that copies your current. There is a non-ideal situation, because as you remember, we had this 1 plus alpha VDS. So if you go to the lab and measure the currents, you won't be seeing that it's exactly what you want, because the VDS of this will be probably different than the VDS of this. And therefore, due to this term, the channel length modulation, your currents won't be exactly copied or scaled perfectly, because we are not having that, but we are having this rather, right? So the scale, due to the change in VDS, will be different. Well, it depends on alpha. Alpha is showing how much this slope is changing, right? So this VDS is a non-ideality factor.